This is a laboratory that we've built to understand the transient performance of air conditioners. Most labs in the world are built mostly to understand the steady state performance of air conditioners. We've built this lab specifically to test transients or dynamics of air conditioners, and that allows us to build models, dynamic models of the air conditioner, and we use those models to develop model-based controllers. We've built this laboratory to test and evaluate control algorithms that we develop at Merle to control room air conditioners and home air conditioners. Each chamber in this laboratory is meant to simulate a room to test a 4-room house. We can simulate from about 0 degrees Celsius to about 50 degrees Celsius. And in the next room, there's another chamber to test the outdoor conditions. We're developing next generation control algorithms for future products that Mitsubishi Electric sells. The control algorithms that we design today are aimed to save energy and improve comfort in customer environments. Most HVAC systems in the US that people are familiar with are on-off type systems. Systems that turn on, and when they're on, they're at 100%, or when they're off, they're off. The kinds of systems that Mitsubishi Electric sells are what's called variable refrigerant flow or variable capacity air conditioners. And that means that the operation of the machine can be dynamically adjusted to match the heat load. And we design control algorithms to more precisely match the heat load. We use simple models of the air conditioner calibrated from this laboratory to predict the future response of these air conditioners and make decisions at the current time that are predicted to be optimal in the future. And by doing so, we can enforce constraints and improve energy efficiency. The control algorithm uses a model to predict the future response of the air conditioner and solves an optimization problem online to compute actuator commands that are predicted to be optimal. The optimization problem is solved iteratively, which means as we collect new information, we can adjust our plan and make improvements as time progresses. So one kind of system that we test at Merle has multiple indoor units. And a problem with an air conditioner that has multiple indoor units is how to manage the refrigerant flow among the different indoor zones. So this is an example of a controller that we've developed at Merle that more precisely regulates the amount of refrigerant for a given indoor unit. So as I play a video, these are infrared videos of a heat exchanger where the blue color represents colder temperatures and the orange color represents warmer temperatures. At the top, there's an existing control method which operates the indoor unit in an on-off fashion. The bottom shows a Merle controller where we more precisely open the valve to let in just enough refrigerant to perfectly match the heat load. And as a result, we can achieve more accurate zone temperature regulation. So we use this computer to monitor the conditions in our laboratory and test predictive controls. This is a series of plots where we examine the performance of the predictive controller. The yellow line represents the current time, and everything to the left is historic recorded data, and everything to the right is predicted data. So I can go over here and change the set point in one of the zones. And the room temperature set point has changed, and now the predicted room temperature response is updated on the screen. Since this is a thermal system, things change slowly, so I've recorded a video offline of the same kind of data. So this data shows pre-recorded information from our predictive controller. Again, the yellow line represents the current time, and everything to the right is a prediction. These are the room temperatures in 2 zones, and as I scrub forward, you can see that a set point has lowered, and the predicted room temperature response will achieve the set point into the future. Another important feature about this type of controller is that it enforces constraints. This signal shows a critical temperature in a piece of the equipment. It must be maintained below a maximum value. The predicted response of this temperature will be maintained below the constraint into the future. And as I scrub the video forward, the actual temperature follows the prediction very well. I'll also point out that both zone temperatures achieve their set point with 0 steady state error. So the kinds of controllers that we're developing at Merle today enforce constraints, and that allows us to operate the machines closer to their design limits. And machines like air conditioners that operate closer to their design limits can be more effectively deployed in wider scenarios. So for example, using this control algorithm, we can deploy heat pumps into colder climates and provide energy efficient means to heat homes without burning fossil fuels. So we have 4 test chambers in this room, test chambers A, B, C, and D, which are designed to simulate the indoor conditions in a house. We also have a test chamber in the room next door designed to simulate the outdoor conditions. Inside each chamber is an electric heater to provide the heating load so that we can test our air conditioner in cooling mode. We also have a chilled water fan coil system to provide the cooling load so we can test in heating mode. So this laboratory really provides us a lot of capabilities to test these air conditioners in both cooling mode and heating mode.
Let's go into the room where it simulates the outdoor conditions and see some of the mechanics of really how we simulate these systems and characterize them. So if we look out here, you can see a lot of the infrastructure that we use to model and describe how these systems behave out in the real world. Here is a big set of control panels for a number of different systems that we have built here in the lab experiments. And over here, actually, you can see a very, very large system that we use to simulate various conditions outdoors. For example, we can simulate if there's a cold day. We can actually turn this on. There's a chiller over here. We can produce a lot of cold water and then pipe that water to many of these other indoor units. If we look over here, we'll be able to see actually the outdoor unit for the systems that we're looking on. So let's go and check that out. When we go to test these systems, we take commercial systems from Mitsubishi Electric and we install a lot of extra instrumentation. These systems are very, very complex systems. So we want to get a lot of extra measurements and data from the system so we can build accurate models and describe the action of these controllers. You can see that we install a lot of extra sensors in the system so we can really understand what's going on. Once we start operating the system, we can then take this data, analyze it, and use it to understand a lot of fine-grained detail and really understand how to improve the performance and maximize performance of the system for a wide range of conditions in this chamber.